going now. So share the screen and where's the image made? This one up here. How do I hit that? All right. I think we're good to go now, right? So, first thing I want to do is I want to go back and revisit power. We kind of talked about this a little bit at the start or at the end of class on Friday, but the time was kind of short, so I rushed through it. So let's go back and kind of look at this in a little more detail, make sure you understand it. So power, really briefly, this is one of the equations that's really easy to derive. We go back to basic principles. We know that work is equal to force times distance. And we know that power is work divided by time. So that's force times time divided by force times distance divided by time. A lot of times we take that distance divided by time and call it a velocity, which equals force times velocity, but we don't really need to take it that far. We want to look at what is the force. Well, if in a pump, what we're doing is we're lifting the water up in the air. And so the force is the weight, all right? So force is just simply gamma times the volume. So this is the total weight of the fluid that we're trying to lift. So now if we go ahead and bring this back in the picture, we can say that power is equal to gamma times the volume times the distance. And we're going to let the distance equal the height, h. Height, or it could also be the head loss, right? Both of those are distances that we're going to move this fluid. We're going to let that equal then this big H. And we also know that the volume divided by time is equal to the flow rate Q. All right, so power then is equal to gamma volume times H divided by time, which then is going to be gamma Q. Allergy season. All right, so that's power of a pump, gamma QH, and then we have to follow the units. And so remember that in the English system, we do power in terms of horsepower, so P sub H sub P, and that's gamma QH divided by 550. And in the SI system, power is in terms of watts, so gamma QH is what we have. Then if we want to go over to kilowatts, power in terms of kilowatts, gamma QH divided by 1000. So this is kind of, we talked about this last part. The derivation is new, but this shouldn't be anything that new to you because we talked about power in physics. Okay, so now the next part. Note that, everyone got that? Good? Or I'll just slide it up here. Okay, here we go. So note, we buy motors by horsepower, HP, and we buy electricity by kilowatts. Okay. Now, first off, I want to note that not all motors are electric motors. I'm sorry, I said that. That's pretty obvious, but not all pumps are electric. We have other pumps that could be diesel, they could be natural gas, propane, gasoline. So we're not going to focus on those that are mechanically driven. We're going to focus on, well, they're all mechanically driven by the motor, but we're going to focus on those that have the power source as electricity, because that by and far is the largest that civils deal with. If you're dealing with an agricultural system, then it could vary. But when we put in a big electrical system, when we put in a big water system, whether that's sewer or drinking water, it's generally powered by electricity. Okay, so that's what we're going to focus on. But the principles are the same. You just have to figure out how much power does a diesel motor, a diesel engine put out. But here's the concern is we buy the motor by horsepower, but then we turn around and we buy electricity by kilowatts. So if we want to go all the way and calculate how much electricity a motor needs, then we need to do a conversion, all right? So I would note that in 1 horsepower, there is 746 watts, or 0.746 kilowatts. That's the conversion factor, okay? Now, if I go ahead and do the conversion, if I want power, so if I'm working in the English system, I want power in terms of kilowatts, and I'm using gamma QH in English system units, then I would have to go ahead and convert by 550, and I would also have to do the conversion of, so this gives in terms of horsepower, and I know that in 1 horsepower, there is 0.746 kilowatts, and if I do that, this whole equation goes to gamma QH divided by 737. So that is the technically accurate equation that if I want to convert English system units as such as the specific weight, such as the flow rate, and this is the flow rate in CFS, and in terms of head in feet, then I'd stick it in that equation and divide by 737 to get it into kilowatts. All right. But in industry, for some reason, people said, you know, that's too hard to remember. So I'm going to put this or power in kilowatts is equal to gamma QH divided by 746. Oh, thank you. Now, the reason they do that is because old timers had this concept stuck in their head that the conversion is 746. 746 and 737 are so close, they call it good enough and move on. So you'll see both equations in books. All right, and so either one will get you within a few pennies of each other. Within the accuracy of being able to define your system. Friction factor is a bigger variable than the difference between those two numbers. So either one works just fine, okay? But I wanted to make that clarification because if you start pulling out books or looking up on the internet, you find these two different equations, you're like, and if you don't understand the history behind it, it's like, what? Why are there different numbers? You think they'd have the same number, right? That's the reason why, all right? And we still have to add now the efficiency of the pump. So if we go water horsepower is equal to then gamma QH divided by 550. All right. Braking horsepower, B sub HP, is equal to gamma QH divided by 550 times the efficiency of the pump in decimal form. And we talked about the efficiency of the pump, pull that off the pump curve, and we'll look at the example today. So water horsepower, braking horsepower, and then total horsepower is equal to gamma QH divided by 550 times the efficiency of the pump times the efficiency of the motor. So E sub P, efficiency of the pump, efficiency of the motor. That's the total amount of power we have to supply to the motor for the motor to turn the pump, for the pump to add that amount of water horsepower to our system. All right. Now, the interesting thing, once again, is this is in terms of total horsepower, but we buy electricity in kilowatts. So we are most likely to convert this and say the total power in terms of kilowatts is gamma QH divided by 737, efficiency of the times the efficiency of the pump times the efficiency of the motor. Okay, any questions from those online?
Is there one that you typically use more horsepower or kilowatt, or does it just depend on the problem?
Usually if you're doing a total problem, this is what we use, okay? Because we also want the economics of our system. And I need to make one other comment here. Remember that this Q here is Q dimensionally is CFS, or unit-wise. I guess I shouldn't put dimensions, it's volume time, but I'm put unit-wise. Units at CFS, but we also buy pumps in terms of gallons per minute. Okay? So I would note that in 1 cubic foot per second, there is 448.8 gallons per minute. And a lot of times we just say 450 gallons per minute, depending upon how accurate you want to be. So if you want to save yourself a couple of steps, you can say power in terms of kilowatts is equal to gamma divided by gamma times Q divided by 550. Whoops, not 550, 450. Times H divided by 737 efficiency of the pump, E sub P times the efficiency of the motor, E sub M, and that then where Q, once again, in this case, unit-wise, is in gallons per minute. So we'd stick gallons per minute over here, go ahead and solve that equation, and that would give us power in kilowatts to figure out how much electricity we need to purchase. Okay? And power in kilowatts is sold as kilowatt hours. So if you use 1 kilowatt for 1 hour, that's what you get charged. Does anyone know what the going rate in Idaho is for 1 kilowatt hour? You guys have never, you probably live in places where you don't have to pay your electric bill, right? It's part of the rent, or you just pay it. It's like, I don't look at it, I just pay it, right? Whatever I have to pay. If you look at your electrical bill, you can see what the charge is per kilowatt hour. And to be honest, I haven't looked at mine recently, but it is somewhere around 7 to 8 cents in Idaho per kilowatt hour. So if you take 100, no, sorry, if you take 10 100-watt light bulbs, because 10 times 100 watts is going to give you a kilowatt, right? So if you take 10 light bulbs and turn 10 100-watt light bulbs and turn them on for 1 hour, it's going to cost you 8 cents. So if you got 10 rooms in your house, put the light on each room, 8 cents. All right. So relatively cheap in Idaho. If you're down to California, you're going to pay 22 cents per kilowatt hour for a whole variety of reasons.
Can you scroll down?
Scroll down.
Or
Oh, okay, sorry. So, okay. All right, so now let's work a problem. Let's bring these concepts together for pumps. So we're given this Given the pump characteristics curve below, so this is the pump curve, select the best impeller diameter for the following system. It is desired to supply, so our goal is to supply 500 gallons per minute in a system with an elevation change of 80 feet. So our delta Z is equal to 80 feet. All right. The pipe is 6 inches in diameter, 700 feet long, with a Darcy-Weisbach friction factor of 0.02. Define the efficiency of your choice as well as the net positive suction head, NPSH required. Now, we haven't talked about NPSH. I'm going to introduce it right here, and then we'll cover it in more detail. I don't know if we'll get to it today or not, but so NPSH, net positive suction head required. Okay, so once again, don't worry too much about that. We'll come back to that. But that is part of our pump curve down here. All pump curves should have the NPSH curve on them as well. So I want to introduce that. We'll come back to it. Okay, so here's our system essentially. We have a little tank down here. We're pulling from that water level. And we're going to run that over through our pump. And the pump's going to lift the water up to some other tank or some other device up here. And there is 80 difference between those two. So the first thing we need to do is put our system curve onto our pump curve. Okay, so you'll remember that the system curve, which we also call the total dynamic head, is equal to delta Z plus C times Q squared. And so we have to calculate C. So we're going to say C is equal to F times L over D times 1 divided by 2G A squared. Okay. Mark, we doing okay?
Yeah.
Okay, all right. So our friction factor then is 0.02 times the length of being 700 feet long, divided by the diameter. The diameter is 6 inches, so 0.05, half a foot, times then 1 over 2G times the area, which is going to be pi divided by 4, 0.5 squared, end of quantity, squared. So if we punch this value in, I get a value of 11.28. So total dynamic head is equal to 80 feet plus 11.28 times squared. And that's my system curve right there. Now we mentioned to plot a system curve or to plot a curve, a general curve, we're going to want to plot 3 points. Okay, so I'm going to come over here and create a little table. I have 3 columns in my table. I'm going to have Q, my flow rate in gallons per minute, and then Q in CFS, and then H in feet. So in order to get this curve down, I know I want to start off with a flow rate of 0. And then I look at my curve here and I say, all right, I'm hoping to hit my curve somewhere in here. So I should probably pick, like 300 or 400, and then maybe somewhere up here in the 700 range to be able to get my curve properly aligned as it passes through those points. So I'm going to pick 400 and 700. probably just as easy pick 300 and 600, or, 350 and 800, whatever. Now I'm going to convert those over to CFS. So 0 gallons per minute is obviously 0. 400. I'm going to turn this 400 into gallons per minute, so 0.89, and 700. Converting that over is going to be 1.56. All right. Now I can go ahead and put these in my equation to find out what the respective head is going to be. So if I put 0 in there, it obviously is 80. That's my delta Z. Okay. And then 11.28 times 8.888 squared. And then multiply that, and that gives me 8.9 feet. Oh, but then I got to add 80 to it. So we're just going to call this 89 feet. All right. Next one, and I get 107. I've done my numbers correctly there.
So for the C, we use S, but then to actually like plot it in our graph, we use it as gallons per minute.
Correct, because most pump curves are given in gallons per minute. And so like I said, I'm going to plot a point here at 400. I'm going to plot a point here at 700. But this equation, my system curve, is calculating Q in terms of cubic feet per second. So I go ahead and do that conversion. Let's divide by 450. Let me just check one of my values here. I'm not sure if I quite got that right. Okay, yeah, we're good. Okay, so now I can come over here and plot those values. Okay, so I'm going to come up to 80. And then the next point is at 400. So 400, I'm going to be at 89. So do my best guess in there. And then at 700, I'm going to be at 107. So 700, I come up to, there's my 100, 120, so 110, 107 is right around in there. So now I'm going to draw the curve. I just missed my points, but okay. I'm going to do a little better job there. All right. Good enough. Okay. So now I say, all right, I have 3 pump impellers that I want to use. And if my target is 500 gallons per minute, okay, I look at both my efficiency and my target flow rate. And note that if I use impeller A, let me blow this up here, oops, wrong way. I know that's kind of a small pump curve and a thick line. But if I pick pump impeller A, I'm going to be operating somewhere out here in the 600 gallons per minute range. And I'm also going to be in the 85% efficiency. But if I pick impeller B, I'm going to be down here near to the 500, and my efficiency is still 85%. So since my target is 500, there's no need for me to pump more than I need, because then I'm going to have to put a valve on there and throttle it. So the obvious choice for this one is impeller B. Okay. So if I choose impeller B, so if I come up here now, actually, well, I gotta be careful. This is actually really good. If I have this drawn very carefully, and a regular pump curve would be a little bigger, I'd probably use a French curve on this, or a flexible thing, a flexible ruler, if you've ever seen those, or I would plug it into the computer program. I could plot this into Excel, and I can find, we'll talk about how to get the equation of this pump curve from the points on the pump curve, and then we could narrow it down a little more detail. But actually, where this is going to operate is where those two cross, which is right here. Okay. So let's look at two. We obviously know that pump C down here is only going to give us about 350, so it's way too low, 350 gallons per minute. Pump B is going to give us about 470. So let's see, I can. So PB is going to be 470 approximately gallons per minute at a head what would you say that was, 93? At H equals 93 feet. I'm looking at it from an angle here. Also through my curved face shield, which distorts things for me. Do you guys agree with that?
I mean, I graphed mine and it's closer to, like, mine is exactly on the 500.
Is it?
And it's like right at 90 feet, but yours looks a little different.
Well, it could be. I don't have my figure very good. But you know what, we're going to use this as a good comparison to kind of show the concept. So I would trust your graph more than mine, Laura, but we'll use it as an example here. And then if I said we were doing pump A, that would give us approximately here, that mine is right on the 600. So 600 gallons per minute with an H, and we're going to call that good at 100 feet. Okay. And the efficiency of both of these is 85%. Any questions on how I'm reading this graph, how we plotted that up?
So when you're drawing the lines down, is that from the, like, I'm thinking your line 10, so is that from the?
So I wanted, I'm sorry, what did you say about the X's?
When you're drawing like the lines down, is that from the curve you drew?
Yes. I'm drawing the location where my system curve and my pump curve intersect. That's my operation point. Okay. So I'm going to go for pump curve A, find that intersection, go straight down for the flow rate, straight across for the head. That's where that pump's going to operate, assuming that I draw a good pump curve. Once again, I don't think that I do have a very good pump curve. It's close enough though. And then B, where that intersects, do the same thing. Okay. Now I don't always need to compare A and B. Sometimes I can just look at it and say, like if it went right through 500, I met my system criteria, right? I've met my system criteria, I'm done. But in this case, we're going to say, can we get by with 470 gallons per minute? It's a little bit less than the maximum we said we need, but we can look at the system and say, you know, we can actually get by, and will we save a little bit of money? And we're going to look. Sometimes you do, and sometimes you don't, actually. Now, in this case, I believe we will, because the efficiency is the same. Usually the efficiency of the trimmed pumps is a little lower. All right. So now we can come back here, and let me zoom out just a little bit. Okay. We know that power, and we're going to use, and this isn't part of the problem statement, but I want to add it in. So we could put up here, also calculate power as part of the problem statement. Okay. So power in terms of kilowatts then is going to be gamma QH divided by 737, the efficiency of the pump times the efficiency of the motor. All right. And let's assume that the efficiency of the motor is equal to 80%, so 0.08. All right, so power in kilowatts of pump B, then is going to be gamma, 62.4 pounds per cubic foot, times the flow rate. The flow rate we said was 470 gallons per minute, and we're going to divide by 450 gallons per minute in 1 CFS, do my little conversion there, times the head, which we said was 93 feet, divided by then 737 times the efficiency of the motor, 0.85 times, I'm sorry, the efficiency of the pump times the efficiency of the motor, 0.8. And that's going to tell me then how much power that pump needs to move that flow. And this tells me then 12.1 kilowatts. Now I can also go calculate the power in terms of kilowatts of pump A. So 62.4 pounds per cubic foot times then 600 gallons per minute divided by 450 times the head that it needs is 100 feet of head. Okay. And divide that by 737 times the efficiency of the pump, which is going to be 0.85, times the efficiency of the motor, 0.8. And do that calculation now. And I get 16.6 kilowatts.
Why don't we calculate the power for C?
Okay. And it's a really good question, but let's come back to our problem statement. One of our design parameters is that we need to supply 500 gallons per minute. So C, which is down here where it intersects, only gives us 350. We know we're way below the parameter. So that impeller does not meet our design parameter. So that one's gone. Pump B, if we're being really strict about our design parameter, pump B, if I've not drawn the curves correctly, does not meet it either. Okay, Laura's does, and this is actually a really good example of design. Where I'm pulling something off of a graph, it's very easy to go either way a little bit, right? I mean, 30 gallons per minute is not that big when I'm pumping 500 gallons per minute. What percent is that? Okay, well, we're talking a 6% error there, 6%. So this is where we need to look at in a little more detail, and it'd be better to draw a better curve, okay? And then look at our system. Was the 500 gallons, does it have a safety factor built into it? We knew that sometimes we may need to go a little higher than that. And if it has a safety factor, if that safety factor is 1.2, well, I can take 6% out of 1.2, 20% over, and bring it down. Because the difference here is quite a bit. But if I absolutely need 500 and it doesn't fit on my graph, I better go to the larger pump or find a different pump. Okay, so let's say I want to operate pump for 30 days at 8 hours per day. I want to find the cost with the cost of electricity. So with electricity at 0.08 cents per kilowatt hour.
Just for clarity, you'd want that to be 0.08. Isn't it 8 cents a kilowatt hour, not 0.08 cents? So that'd be, yeah, thanks.
So. So now the total dollar amount that I'm going to pay is going to be equal to 30 days times 8 hours per day times, and let's use pump B. Let's assume that pump B is the one that we're good with. Okay. So 30 days times 8 hours times then 12.1 kilowatts. And then we're going to multiply this by 0.08 dollars. Oh, I should have put, go back here. It's 8 cents per kilowatt hour, not 8-cent kilowatt hour, 8 cents per kilowatt hour. It's a pretty important distinction right there. So 8 cents per kilowatt hour. So over here, I'm going to put the kilowatt hours on the bottom side. And so now my total cost, let's see, hours is going to cancel out, days cancels out, kilowatts cancel out. What I'm left with is dollars right there. Okay, so I can go ahead and calculate that. So this is going to give me a dollar amount then of $232.32. That will be my operating cost for that pump in this current system.
And why did you choose the overhead?
So I'm just going to assume that the 470 is close enough to my target of 500. That's a personal decision that I made. I'm going to say, yeah, it fits the criteria within my design parameters. I could do the same thing. You know, if I wanted to calculate pump B, crank that out here really fast. And obviously did something wrong there. Let's do this again. $318. So pump B, I'm sorry, pump A would be $318.72, and really shouldn't be putting the cents on there because I used a graph to pull this off of, and for me to assume that I can actually grab the values, act it down to the pennies is pretty presumptuous. So, you know, 320, 232.
The efficiency of the motor, is that usually given, or do you
Excuse me.
let's see,
Thank you.
find that from the
Yeah.
graph somehow too?
So the efficiency of the motor is something that the motor manufacturer would supply.
Okay.
So when you look at the pump curve and the company, they tell you this is the motor that goes with this pump, and they would tell you that that's what the efficiency.
Okay.
And the efficiency of the motor does not change within a reasonable range of where that pump's being operated at. So let me come back to the pump curve here. So even if I'm operating on C, or if my curve actually went up like this, my efficiency of my motor does not change. The efficiency of the pump changes, but the efficiency of the motor does not. Okay? Other questions on this?
So for Homer,
Mhm.
will we be given the efficiency of the motor, or should we just assume like an 80%?
I will give you the efficiency of the motor unless I forget. And if I do, assume 0.8, because that's pretty reasonable. Yeah. Okay. So coming back to our problem statement, we defined which pump we want to use. now what we need to do is find the net positive suction head required, NPSH. And we've got the graph down here. And we can come down and we would follow that graph down, depending upon where your system curve and your pump curve intersected. And I would come down and intersect with the net positive suction head. And then I would take that over to the side. I'm not drawing a very straight line, but I can then say that the net positive suction head required is equal to approximately 10.5 feet. Okay. Now there's some other values on this pump curve. And this is the brake horsepower. Some pump curves have them, others do not. So this is basically saying, I'm going to do a calculation for you, and I'm going to calculate the brake horsepower. And this is supposed to be just a kind of quick and easy, how much brake horsepower do I need? Remember that the brake horsepower is equal to gamma QH divided by 550 times the efficiency of the pump. So if we go ahead and do this calculation, 62.4 pounds per cubic foot times our flow rate of 470 or 500, whatever, which one you pick. I'm going to divide that by the 450. And then I can multiply that by the amount of head, 93 feet, and divide that by 550 times 0.85. Doing that, is approximately 13 horsepower. I come down here and intersect that curve on B, and I come over right here, I should get, I can draw a straight line, not quite straight, but I should get 13, which is it does. Okay. So this way, this allows me to do a quick calculation or a quick idea of how much brake horsepower I need without doing any calculation. I just keep bringing my line straight down, intersect impeller B because I selected B, come over there and say, okay, it's about 13. And knowing that it's 13 now, that'll help me go find a motor that will be coupled with this, because I know how much power the motor needs to supply. It needs to supply 13 horsepower.
How did you get the 10.5 for the other one?
Okay, so yeah, that's a good point. Let me blow this up, because be careful with these graphs. Too far. These pump curves get kind of weird as far as they put stuff all over the place. And you want to make sure you read it correctly. The net positive section right there that I've kind of, this is tied to this little side graph right there, that little axis. And the brake horsepower down here is tied with the brake horsepower over there. So I want to make sure that I read off of the right axis on this graph. So in this particular graph, I have one x-axis, 3 y-axis. Okay. Okay. So where we're going to take this. So today we basically figured out how to put the system curve on top of the pump curve, find the operation point, and using the operation point, find the efficiency of the pump and the head and the flow rate that it's operating at and the head that it's operating at. And we've also found the net positive suction head required. And we don't know what we're going to do with that yet. That'll be Wednesday. But we've been able to find that bit of information off of our pump curve. We've also been able to calculate, if we know the cost of electricity, we know how long the pump's going to be on for, we can calculate the cost of operating that pump. Those are the topics that we covered today. Any questions on those? Okay, I will post a homework set for you. Have a great day, and we will see you on Wednesday.
Have a good day, Dr. Bruce.
All right, thank you. You too. Okay, we'll see ya. If I get a chance, I'll try and come down there, work on the culvert, but
Random question.
okay.
That's not related to what we've talked about.